So at that point, you would be forgiven for being skeptical if self-driving cars would ever, fully self-driving cars on the real road would be practical even within our lifetime. But we've come a long way since then. There's on the other side, the contest did jumpstart a big wave of research and development that really has continued on through the present. Then on the other side, there's always optimists. Probably the most prominent is Elon Musk from Tesla, who's been claiming that we would have fully self-driving cars in 2 years for about the past 5 years now. And last I heard, he's calling for 2020. But between those two extremes, where are we really right now? Probably the most well-known is Waymo, which is a subsidiary of Google that's been working on self-driving cars for a number of years now. And they've accumulated over 10 million on-road testing with their self-driving prototype cars. And they actually recently started offering a limited self-driving taxi service in Phoenix. Beyond Waymo, most of the big automotive companies have major R&D programs going on in the area of self-driving, as well as numerous large and small high-tech companies have jumped on the bandwagon. And IEEE obviously is interested. They even have a dedicated newsletter called Cars That Think, which is a bit of a misnomer. Cars don't actually think, they just think that they do. But that's a philosophical discussion for another time. So for tonight, we'll just go with Cars That Think. Anyway, there is definitely a lot of interest and also career opportunities for engineers, which is always a good thing. But we've got to the point where computation is really the limiting factor now. The sensor technology and control theory and actuators and things have been pretty capable and well understood for a while. So the bottleneck is being able to interpret the data from all of these sensors and comprehend the environment around the car to the level necessary to support full self-driving. And it's only recently that the available computational power, both hardware and software algorithms, have been approaching the level that would make self-driving possible. Another important category of smart cars is driver assistance, or advanced driver assistance systems, or ADAS, which applies much of the same underlying technology to a little bit less glamorous goal of assisting a human driver. And this is technology that's actually become fairly well established over the past few years, and a lot of driver assistance features have become widely available in cars that are on the market now. The driver assistance features can broadly be categorized as safety features that either will alert a driver when a dangerous situation is approaching, or actively step in and take control and try to avoid a dangerous situation, like automatic emergency braking. And other features that are convenience features that just automate aspects of driving that can be tedious or tricky, like parallel parking and things like that. So probably fairly obvious, but why does this sound appealing to a lot of people? The convenience of being able to use your commute time more productively. If you've ever been in a situation where you have a long commute in rush hour traffic, the idea that you could use that time more productively than just watching the car ahead of you is pretty appealing. There's also the potential to improve mobility for people who are disabled or unable to drive themselves for whatever reason. And there's also lots of applications in transit, like the idea of convoying freight trucks on the road. So one driver could lead a caravan of trucks that are driving very close together, so they have lower wind resistance and better fuel economy. Also, at a more local level, parcel delivery robots, instead of having a UPS truck, a little self-driving robot could go out into the neighborhood and drop off packages. Lots of ideas like that, and also some a bit more more dramatic ideas to make a more drastic change in driving. We're seeing already beginnings of a transition from individually owned cars to ride-hailing services like Lyft and Uber, and fully self-driving cars could even further accelerate that transition. Self-driving cars with ride-hailing could make the public transportation systems more effective and more usable. You can easily get a ride to the train station or bus station or to your destination. That becomes more practical for a lot of people. There's also the idea of smart cities and vehicle-to-vehicle and vehicle-to-infrastructure communication, where cars can wirelessly communicate their intentions and their surroundings to nearby cars on the road, and also communicate with the infrastructure, coordinating traffic to reduce congestion, or even identifying where available parking spaces are instead of driving around the block over and over again. Lots of things that could make big changes to how we go about transportation. Possibly the biggest thing is safety. I'm sure you've all seen statistics like this. There's a huge number of fatalities and serious injuries caused by traffic accidents, and the vast majority of these are caused by driver error. And in theory, self-driving cars, if they reach the appropriate level of safety, could avoid most of these accidents and save lives and injury, and also the large economic impact of the accidents beyond the human lives and injury. So, if safety is the big deal, that naturally leads to the question: are smart cars really safer? At least yet. We're discussing this briefly before the meeting. People have to be convinced that cars are safe. Both the consumers and regulators and insurance companies all need to be confident that it really is safer before it's going to become really widely accepted. And you probably have seen there have been a number of serious accidents that have made the headlines in the last few years that naturally could call this into question. The first one that was widely publicized in the U.S. Was that in 2016, a Tesla car with their autopilot system crashed into a tractor trailer that was turning left in front of it. This one particularly caught my attention at the time, because at that time, Tesla was using processing chips, computer chips from Mobileye, which is a big customer of MIPS. And I was working at MIPS at the time. So kind of opened my eyes a little bit to realize a project that I had worked on had actually been involved in a fatal accident. So fortunately, it didn't seem to be any hardware problem with the microprocessor, but it's still, still not nice when you hear things like that happening. And it seems that this accident seems to have triggered a falling out between Mobileye and Tesla. Shortly after this, they announced that they were parting ways. So the next accident was another Tesla accident in California about a year ago. A car on autopilot crashed into a concrete barrier at a highway exit. There have been a couple of other Tesla accidents that were non-fatal. Somewhat ironically, two of them, the car on autopilot failed to slow down and brake and crashed into a stationary fire truck that was attending another accident. So, not what you want to do when you're out on the road. And the last one I have listed here was a self-driving test prototype from Uber that struck a pedestrian about a year ago. So all of these things really, when stories like this are in the news, that naturally raises questions: are self-driving cars as safe as they are cracked up to be? The fact that Tesla settled a lawsuit over the safety and capabilities of their autopilot system also naturally brings this into question. So it may seem like I'm kind of picking on Tesla here, and that's not intentional. The problem with Tesla is that they are aggressively pushing the boundaries of what technology can do. So they naturally are the ones that run into problems, first of all, and they're also, for marketing and other reasons, tend to seek a lot of publicity, so whenever something happens, they naturally get the publicity for it. So so they've been in the news a lot, but they've also been doing good work, so I don't want to bash on them too much. But from an engineering point of view, based on the investigations that have happened after these accidents, there's actually some technical issues that have come to light that are interesting that contributed to these accidents. In the first two accidents, inadequate vision processing from the computer vision system seemed to play a role. In the first accident, the computer vision system seems to have mistaken the tractor trailer for an overhead sign and expected that it would be able to safely drive underneath it. In the second accident, the unusual road lane markings at the exit ramp seem to have contributed to confusing the navigation system. Another issue is that driver assistance features that individually are okay can be used together for, in particular, adaptive cruise control and lane centering. Together makes a rudimentary self-driving system that in normal circumstances works pretty well until your luck runs out. One particular issue with those systems, it seems commonly the radar systems that they use for the adaptive cruise control as a design choice ignore stationary objects when you're driving at high speed, which for an adaptive cruise control system by itself is probably a reasonable choice if the driver is steering and watching the road, and it avoids false positives from overhead signs and stationary objects along the side of the road. But when you put it together with a lane centering system that is operating in isolation, not coordinating their efforts, and particularly if you're following behind another car and the car ahead of you swerves to avoid a stationary object, these systems seem to be pretty vulnerable to charging straight ahead into the stationary object. And I kind of alluded to the next point. Obviously, they work well enough that drivers become inattentive and complacent and expect them to be more capable than they actually are. And marketing arguably contributes some to this as well. But also even more scientific investigations, I guess you could say, have raised the point that really partially self-driving cars arguably are not safe because drivers, humans, naturally become inattentive when things are behaving normally and only become attentive when they see a sign of danger. And in driving situations, that comes up too quickly for somebody who's not paying attention to what they're doing, and humans don't respond quickly enough to resume control. One other factor in the Uber incident, it seems their prototype self-driving system, again as a deliberate design choice, was disabling the automatic emergency braking feature on that car because it was causing too many false positives, and they expected that their self-driving system was capable enough to do without it at that point. And it seems that the automatic emergency braking system may have been able to avoid the accident if it hadn't been disabled.
Can I ask a quick question?
Yeah, sure.
The inadequate vision processing,
Yes.
it makes it sound like maybe it wasn't fast enough or something, but was it really a computational capacity issue or was it a recognition issue?
It's some of both. I think it's really
training these things,
right.
Can be very hard.
Right.
And sometimes you think you got to train something that just a tiny bit off that you as a human wouldn't recognize.
Right.
Will get miscategorized.
Right, and we'll actually be talking about that a little bit more a little further on. But really, yeah, you're right. The real thing is the recognition. Now, with more powerful processing, you can train more and be ready to recognize more things. But really, it's the recognition that's the issue here. So, engineering lessons. What can we do to improve this situation and avoid these problems? And really, I shouldn't say how can it be fixed? It's how is it being fixed? This isn't some new idea that I'm proposing tonight. These are things that the industry has been working on for the past few years. Obviously, continuing improvements in computer vision, hardware and software. Improvement is always better, and there's always going to be room for more improvement. The next point is sensor fusion, where you combine the inputs from multiple sensors, such as multiple cameras, radar, LiDAR, and use those together to form a combined view of an understanding of the environment around the car. And then that combined view of the environment is used for centralized control of all of the driving features, rather than having independent features that operate on their own in isolation. And like I alluded to earlier, there's the idea that partially self-driving cars may be a bad idea. Maybe it's better just to go straight to full self-driving cars. Several companies, notably Ford and Volvo, have made announcements that they're going to skip partially self-driving as an intermediate step and go straight to full self-driving cars. And kind of amusingly, Ford reported that during some of their testing programs in their self-driving program, they actually had a real problem with their test drivers falling asleep. So that seems to have played a part in them deciding to go straight to full self-driving. Yes?
Hasn't the SAE or somebody come up with like 5 levels, I think, of
Yes.
driver assistance? And so it seems like you wouldn't want to skip the previous 4 to get to level 5. Maybe the automatic braking and lane keep assistance and adaptive cruise control you might want early on before you go to full self-driving.
Right. I didn't actually go through all those 5 levels in my talk because it's too long already and I didn't have time to make it shorter. But yes, that's a good point. It's really level 3 is probably the one that would be most compelling to maybe skip. Level 4 is pretty much self-driving, but the car, if it encounters a situation it can't handle, should be able to pull over and stop safely or something rather than just carrying on. So that probably is safe even without going to full level 5, but yeah, level 3 is the more questionable one. So all of these ideas, of course, require increasing computational power. So as a computer designer, that's always a good thing. And of course, these more powerful processors that would be taking a larger role in driving also need to be reliable so that they don't themselves introduce extra risks. Yes?
Will you be getting to the energy burden of all of this self-driving stuff? And how much does it affect the mileage of the car with all the instrumentation and computation?
I didn't really go into that in the talk. Right now, it's probably a bigger deal that the self-driving systems, like one particularly that is made by NVIDIA that uses a couple of graphics processors to power self-driving. They use a lot of power, and so I think it's still we're in the early stages where we're just getting the first within the last year-ish getting hardware systems that people think may be able to do self-driving. So as that progresses and people design more optimized chips that are more targeted for self-driving, I think the power demands will go down some.
Do you know what the power demand is now? I realize it can get better and better integration.
I don't have really good numbers off the top of my head. The graphics processors from NVIDIA I think are like in the over 100 watts per chip with a couple of those on the board kind of thing. The Mobileye processors that I'm going to be talking about a little bit more are, if I remember, I think they're like single-digit watts or somewhere in that kind of ballpark. So there is definitely, once there's a big enough market to really do more optimal chip designs for this, there is definitely scope to reduce power.
And the LiDAR and the other sensors, do those draw a lot of power?
That's getting more out of my area of specialty, but yeah, I would assume that they do and can be optimized as well. Getting on to the subject of computing, which answers the question of where does MIPS come into this picture. I know I talked to at least one person earlier today that's heard of MIPS before. If you're in the computer industry, MIPS has been around for a long time. Originally it started out from a research project in John Hennessy's group in Stanford, and was very influential in popularizing the RISC style of computer architecture in many families of microprocessor designs since then. It's gone through a series of ups and downs in terms of business. It's been acquired by a number of companies with periods of independent operation and existence in between those. Silicon Graphics, probably most notably from the 90s, and then more recently Imagination Technologies, and just last year now Wave Computing, which is an artificial intelligence startup that acquired MIPS for microprocessors as well. Currently, MIPS CPUs actually power about 80% of ADAS-enabled cars. A couple of our prominent customers that play a big part in that, Mobileye, that I mentioned earlier, does vision processors for driver assistance in self-driving cars, and they've been using MIPS processors in 4 generations of their automotive chips. There's also a company called Valence that does HD-based T networking for in-vehicle networking, and they use MIPS processors as well. So those are just 2 examples of customers in automotive. And the I6500-F processor, which is the main focus of the talk tonight, which was released in 2017, is certified as, according to the ISO 26262 functional safety standard for automotive use, and is used in the Mobileye IQ5 chip, which is their latest chip that's going to be coming in cars in next year. And there's a block diagram on the right of that chip from Mobileye, and I've highlighted the MIPS I6500-F parts of that chip.
So is Mobileye the name of the company?
Actually, I forgot to mention, yes, the Mobileye is the name of the company. They've been acquired by Intel a couple of years ago, actually, and the rest of Intel's automotive efforts have been kind of folded under the Mobileye group at Intel. And their chip is called the IQ.
Just a quick question.
Yeah.
To put this in perspective, is this package can you put in a car passively or actively cooled?
It's actually used in different capacities, and also previous generations of the IQ chip series. They have both. A number of automakers use them for driver assistance or as part of their driver assistance systems in cars over the past few years. They also sell an aftermarket add-on system that you can get from Mobileye for driver assistance. I believe it mounts on your rearview mirror, and the camera scans the road ahead of you and can give you warnings or things. So they're used for driver assistance and for upcoming more capable, more self-driving systems as well.
So what I hear you saying is they're passive. You know, if I look at the box, am I going to have fans on it? Am I going to have water run into it? Or is it just sit there with it?
So these ones, the Mobileye chips are lower power. Like I mentioned, that's one of the things that they claim. One advantage they have is they're low enough power. It can go in a little box that goes on your rearview mirror in your car. Whereas the NVIDIA ones, burn hundreds of watts. They have to be in the trunk or someplace.
Right.
Yeah, you actually answered, but these are intended to be in the cockpit environment, like 85 degree maximum, not under the hood where it's.
I would think so. Yes. I'm not as familiar with that aspect of it, but yeah, I think so. As far as the applications, so the Mobileye chip is really a vision processor chip. So it's up to the car manufacturer and the other suppliers that they work with, whether that vision processing feeds into different types of driver assistance features or a more full self-driving. This is just the vision processing component in whatever the larger system is. Before I go into more detail about the MIPS processor, I want to take a little bit more of a look at the computational problem that we're actually trying to solve. So in simple terms, you need to collect data from a variety of sensors that each one has its own strengths and weaknesses. Cameras, radar, LiDAR, and ultrasound are the most common ones for sensing the environment around the car. You also want sensors to monitor the motion of the car itself, odometric sensors and accelerometers and things like that. And then you can also make use of external connectivity, GPS for location, the vehicle-to-vehicle and vehicle-to-infrastructure networking that I mentioned earlier. And you need to put all of this information together and interpret it and comprehend the environment well enough to plan and execute a course of action to drive the car or assist the driver. So all of that is a lot easier said than done, but that's the goal here. This is a representative diagram of the computational flow for self-driving. I say representative each company that's active in this area kind of has their own secret sauce and wants to keep their technical details close to their chest for competitive reasons. But there's some common threads, and based on what information is publicly available, this seems to be a fairly representative approach. So the first step is perception, which is also the most computationally demanding task. This is taking in data from the sensors and interpreting what you see. And I'm probably focusing most on camera and video type of sensors, but radar and LiDAR and other sensors would have a similar process. The first step in this process is pre-processing, which is more conventional image and video processing algorithms. It could be things like de-warping, stitching together two images from adjacent cameras that form a wider field of view, and things like motion detection and things that can be done with more conventional image and video processing algorithms. Then the next steps, almost pretty much universally, are done by neural networks. Object detection and recognition is taking a digital image and picking out from the image, there's a car in there, there's a bicycle, there's a street sign. And then once you've identified some objects, it's important to be able to track their motion, their trajectory, and predict the trajectory. And that also can use neural networks. So the output, once you've analyzed the data from the sensors and made some sense of it, then that goes into the sensor fusion and localization. Localization is the process of identifying where the car is in the whatever model you've got from your perception flow. This is an area where there is some variation from one implementation to another. There could be some localization mixed in with the perception step, or exactly how they divide things up can vary. And the fusion and localization can also make use of connectivity and GPS data and predetermined map data as well. Once that's done, then that goes into the trajectory planning and driving policy, where you identify a safe path for the car to take, and then from there control to actually make the car take that path.
Do the different perception blocks share data back and forth to help with the object detection recognition?
It can vary a little bit. As I understand, it's fairly common, like, for multiple cameras to feed into one perception block. But I think like radar and LiDAR would be processed separately, and then the fusion happens after the initial perception step.
Yeah, right. There are now several 75 gigahertz single chip radar with processing, which probably will go to do the whole left blue box.
Right. Yeah.
Yeah.
Yeah. Okay. So neural networks play a big part in the perception and other parts of self-driving. And neural networks are a powerful general-purpose approach to computing that their strength is really complex pattern recognition. So they're widely used not just in automotive, but in all kinds of computer vision applications, OCR. Also things like machine language translation from automatically translating from one language to another, fraud detection in credit card transactions, all kinds of different things. The basic computational element of a neural network is referred to as the neuron. There's a diagram of that in the lower left-hand corner. It has a number of inputs, and it multiplies each input by a predetermined weight. So if an input has a higher weight, that means that particular input has a larger influence on that computation. And then it performs a weighted sum of all of the inputs plus a bias value from that neuron to form a preliminary value, and then that value is put through what's called an activation function, which is a nonlinear function that typically is a sigmoid type of shape, like what's shown in the center diagram there, which in this case saturates at higher values of the input saturate to 1 and lower values saturate to 0, and there's a kind of linear range in the middle that maps the value to a more linear range. So these neurons are connected together to form a network. There's a simple example on the right-hand side. The input layer doesn't actually do any processing. It just feeds whatever input it gets to the next layer. And then there can be a hidden layer that does not directly connect to the inputs or the outputs. And then the output layer is the final layer. The output from neurons in that layer is the actual result of the neural network. By appropriately selecting the weights and bias values in the network, and also the number of layers and the number of neurons, the connections between them, you can solve very complicated problems with neural networks. The output from a neural network can be used for two types of problems: classification, where you're just dividing things into groups, like identifying in your image whether you have a bicycle or a street sign or pedestrian, and regression, which means estimating a value from a continuous range, like estimating the distance to the car ahead of you, something like that. Once you've set up a network, chosen how many neurons and how many layers and that sort of thing, which is a bit of a black art in itself, people who have expertise in that are really in demand. But once you've selected the architecture of your network, the training process is how you set the weights and the biases, and that uses what's called the backpropagation algorithm, where you run lots of training data through the network and then calculate the error compared to what the expected or desired output is, and then feed that error back through the network as an optimization algorithm to select the weights that will minimize that error. And then if all goes well, once you've optimized the weights for your training data, they should also be applicable for more general use as well.
Are these neural networks, they're typically hardware accelerated?
We'll get into that a little bit more in the next slide. At this level, I mean, it's a computing process, so you can write a program on any computer that will solve a neural network, or you can accelerate it by designing more specialized hardware for it. We'll talk about that in the next slide.
Okay.
There's a couple of types of networks that I just want to quickly mention that are important. You may have heard the term deep learning, which is a popular buzzword lately in artificial intelligence. It just means using a neural network that has multiple hidden layers. So a deep neural network has multiple hidden layers, and that's called deep learning. A kind of neural network that's very useful in image processing and video processing is called a convolutional neural network. Now the key insight here is that if you're looking for an object in an image, like say a bicycle in an image from the camera, the patterns you're looking for to recognize a bicycle are going to be the same whether the bicycle is in the lower left-hand corner or the middle of the image or where in the image this bicycle is. So rather than taking a brute force approach where every pixel of the image feeds into one neuron and you end up with a very large network, you can make a smaller subset that's called a filter that, for example, could be like 5 by 5 of weights for that small region, and then you scan that across the image. So you're reusing that same section of the neural network to look for the same pattern across the image. And that mathematically works out to be a convolution algorithm, a convolution operation. So networks that do that are called convolutional neural networks, or CNNs. The other type of network that's very important in automotive applications is a recurrent neural network. And they use either some feedback or some memory within the network to be able to recognize and predict patterns in sequence or time. So this is very useful for the trajectory prediction. Like if a child is running down the yard and goes behind a parked car at the side of the road, you can predict based on memory that they might emerge from behind the car onto the road, even though a convolutional neural network wouldn't see the child because it's just looking at one image at one time and doesn't have any history. So getting to your question, how do we implement this in hardware? So a neural network, the neuron is performing effectively a dot product. It's summing up a bunch of sum of products. So if you organize your data appropriately, a neural network layer can be represented as a matrix multiplication. So computer hardware optimized for matrix multiplication is very effective here. There's a number of different common structures that are commonly used. A coarse-grained reconfigurable architecture is the specialty of wave computing that has acquired MIPS, and they're targeting various artificial intelligence applications. That's basically a two-dimensional array of simple processing elements that are connected in a grid network. Some of the other ones, graphics processing units like the NVIDIA GPUs we were just talking about, digital signal processors, FPGAs, and systolic arrays can all be used to efficiently implement neural networks. So these type of computing engines are great for repetitive calculations on regularly structured streaming data, but they're not so good for decision trees and random control logic and interrupt handling. So the approach that's normally used is you have a general purpose CPU that does the coordination and control, and then one of these more specialized compute engines as the accelerator for the hardcore number crunching of the neural networks and other calculations. And so when you're using a general purpose CPU as the kind of controller, you want to balance the performance between the CPU and the other accelerators so that neither one is spending a lot of time idle waiting for its companion to catch up. You definitely want efficient data sharing when the neural network accelerator finishes its calculation. You don't want both of them to be waiting a long time while data is being passed over to the CPU or vice versa. And it turns out that multi-threaded CPUs which the MIPS processors are multi-threaded, are very effective for this type of application where you're doing control and coordination of these more specialized hardware accelerators. Now, I'll explain that in a bit more detail. Simultaneous multi-threading is a way of running multiple software tasks concurrently on the same processor. So what happens, it's kind of illustrated in the gray diagram to the right. The small rectangles represent assembly language instructions, and different colors are different tasks that are running or different programs that are running on the processor. So each thread has its own program counter and register file. So to software, it looks like just an independent processor that's running that program. And in the processor pipeline, there's a scheduler that selects instructions from the different threads to execute in the pipeline. So if one program has a high latency instruction, like it's accessing data that is a cache miss, the data is not in the processor cache and it has to go out to off-chip memory to get that data, rather than stalling the whole processor, it can just continue making forward progress, executing instructions from some other tasks while it's waiting for that data to get back. So this is very effective at hiding the memory latency. The speeds of processors over the past couple of decades have increased much more rapidly than the speed of memory. So off-chip memory is now very slow and relatively and very high power energy. So avoiding off-chip, hiding the latency of off-chip access is important for performance. And we've seen typically by multi-threading, we can get about 40% more performance from a processor with about 10% extra area. So that's a good trade-off. In applications where you're controlling these hardware accelerators, you can also get very efficient context switching. So if the processor has multiple threads, you can have, if you have a high priority task on an accelerator, you can, with very little hardware overhead, you can have one thread dedicated waiting for that task to finish. And it's not using up execution cycles in the processor pipeline, but then when the accelerator finishes its task, that thread can instantly respond. It doesn't have to go to an interrupt handler and do a software context switch or anything. So that's very effective in this kind of application. The one other feature that is really important here is cache coherence. So in general, multi-processor computing, cache coherence is a technique where if one processor has some data in its local cache memory, and it may have written that data, it has a modified value, so the underlying main memory off chip has some stale previous value in that location. So now if a second processor tries to access that memory location, if it just reads the data from the off-chip memory, it will get a stale value. So there's hardware mechanisms where the processor can actually get the latest copy of data from the cache of the other processor that used that location. And the MIPS processors have a feature where we do cache coherent I/O. So not only another processor in the system can access cacheable data, but these neural network accelerators can efficiently get data out of the processor's cache. And so it makes a very efficient way to pass data back and forth between the processor and the accelerator without going through the off-chip memory.
So what's the data width for the cache?
64 bytes for one cache line. And the bus is smaller, it's 128 bits, so it takes 4 beats of data to transfer one cache line at the processor level. So some more details on the i6500 processor. It's a 64-bit MIPS processor using revision 6 of the MIPS instruction set. It's not a cutting-edge high-performance processor. It's targeted more of a mid-range processor with power-efficient performance. So it's a 9-stage in-order dual-issue pipeline. So it doesn't get the performance of a longer pipeline with out-of-order issue, but the like the Intel and AMD processors. But the power scales up much more rapidly than the performance when you go to those more aggressive techniques. So in applications where low power is more important, this is a better trade-off for those kinds of applications. And just some other quick buzzwords. It has IEEE compliant floating point support and 128-bit SIMD support. This isn't where you can use the processor data path to perform multiple operations in parallel. So if you're dealing with 8-bit data, instead of just doing one 8-bit operation at a time, you can perform 16 8-bit operations in one instruction. So for the i6500F, we've added a number of safety features onto the previous generation i6500 design, which I'll talk about more in a little bit. That kind of brings functional safety and certified safety to a new level of reusable IP products. That this was the first product of 64-bit synthesizable microprocessor that is safety certified. In the baseline system, it comes in a cluster of up to 6 CPUs that are sharing an L2 cache. If you want to go beyond 6 CPUs, we also have optional multi-cluster support where each cluster would have its own L2 cache that would be shared just within that cluster. It's a synthesizable RTL product, so I don't know if is anybody in here not familiar with what Verilog is? Okay, the Verilog is, it's a hardware language, so it's kind of comparable to a programming language like C, but it has extra details to specify how the circuitry should be implemented. And then the customer is responsible for taking that, what's a sort of a behavioral description and doing logic synthesis to come up with the actual transistor circuit to implement that microprocessor. We provide, there's commercial EDA software that does this, and we provide example scripts and constraints to drive those tools to get an optimal result. But it's really up to the customer to implement it for whatever manufacturing process they want to use, whether it's like a TSMC is probably the most common now, but it could be 28 nanometer, 16 nanometer, 7 nanometer. That's up to the customer.
So does Tesla, I'm thinking, if you're Elon Musk, where are you in the stack of designing all this stuff and selecting and so on? How does that come together as a commercial proposition?
So they are basically kind of 2 levels removed. So our customers would be designing and fabricating actual chips. So like our Mobileye, which is our customer, in earlier generations of Tesla bought chips from Mobileye to put in their systems. Now Tesla is using NVIDIA chips. I think I've heard that they are maybe looking into designing their own chip, but I haven't heard if that's actually reached production yet or where that is.
So they're specifying a chip and then doing the programming for that chip once they get the set back.
Right, right.
Okay.
And so since it's synthesizable, that leaves the option for the customers to have some flexibility in a lot of configuration options like the number of processors, the cache sizes, a lot of optional features that they can include or leave out depending on their application needs. So looking beyond just the microprocessor itself, the cluster shown here, like I said, the processors share an L2 cache, and we use a directory-based cache coherence protocol. The directory is implemented in the L2 cache. And the main memory port is a 256-bit port that goes out to the DDR. And like I mentioned, the coherent I/O accelerators, we allow the neural network or other accelerators to connect through what we call an I/O coherence unit, which is just a kind of an adapter that allows them to have coherent access to the L2 cache and any L1 caches of the processors in the cluster. And like I said, that can be expanded to support multiple clusters through an external coherent interconnect that uses the ACE protocol. One important thing I want to point out that will become important a little bit later is the cluster power controller, which is a block that, to save power, we have the ability to power down an individual CPU if it's not being utilized. You can shut the power supply voltage off and take it offline and then bring it back online later if the demand is increased. It also has the ability to change the clock ratios to each of the processor independently, so you can optimize it for the performance and power you need dynamically as the system is running. And there's some other blocks like the debug unit and interrupt controller that also make up the cluster. So once we have a multiprocessor system like this, how do we go about making it safe for automotive applications? And this is, has a lot in common with the traditional reliability, availability, and serviceability from mainframes and big iron servers. But there's also some key differences. So as you would expect, we use redundancy for fault tolerance and error correcting codes to error detection and error correcting codes to deal with particularly soft errors in the memories. But some key differences in an automotive application, the goal isn't just to avoid any data corruption at all costs. Or at least that's not the primary goal. The primary goal is to avoid a dangerous situation. So any particular fault or error could have a different level of risk and severity of a potential accident it could cause, and also potentially the ability for the driver to compensate and avoid an accident if something goes wrong. So those factor into the risk assessment in a driving application. There's also the notion of a fault-tolerant time interval. So, compared to microprocessor time, cars are large physical objects with a lot of inertia, and so the time constants are larger. If you have a car that's driving down the road on a safe trajectory, there's not really very much you can do in 1 microsecond that can put it into a situation where an accident's unavoidable. So if an error is detected, you have, from a computing time scale, you have some time to try to do something about it. So that makes a difference as well. The fact that the MIPS processors are a synthesizable IP and not an actual chip also has consequences for us. Many of the important variables that are critical for safety are out of our hands. Like I mentioned, we don't control the fabrication process or what process corner our customer is using. The operating conditions, temperature, electrical margins, even things like the clock frequency, clock jitter, power supply voltage, and signal integrity, all of those things are out of our hands. So we have to approach that by documenting our assumptions and any requirements for these areas for the customer, and then it's their responsibility to assess that and deal with it appropriately in their design. Another factor is the CPU is a general purpose product. It's not designed for one particular automotive application, so the safety implications will depend on what you're using the CPU for. So with that in mind, the safety features we added, so we started with the baseline CPU has some features that actually contribute to safety, like, yes?
Do you have any merchant semiconductor companies as clients? Are we gonna see these parts on the market?
I'm not aware of one for this particular one. Microchip PIC32 processors are MIPS processors that are used in a lot of things. That's probably the most prominent, where you could just go buy a chip that has MIPS in it.
Thanks.
So, like most microprocessors, we have TLB-based memory management with read, write, and execute permissions, and also privilege modes like guest and kernel. So, whether a software bug or possibly a transient hardware fault, an alpha particle corrupts some memory, if that would cause the software to try to access a hardware resource that it doesn't have permission, or an area of memory that it's not supposed to be accessing, that could be caught and taken exception already. The baseline processor has ECC protection on the cache memories and parity protection on the data buses within the cluster. It also has a watchdog timer that can signal an interrupt or a reset if software doesn't respond within a specified time interval.
So if you get a parity error on the data bus, does it get fixed in the hardware? You get recycled, or you get an interrupt and you have to go off into a software
So
routine?
the bus parity error will take an exception. You'll go to a software bus error exception handler.
I have a question.
Yeah.
So, cars running this system, back in, all the way up to the Ford Automotive Tech, he's got his OBD2 scanner.
Okay.
He plugs it in to the OBD2 spigot. From your experience, what are your end users providing, just in a general sense, for those people to be able to diagnose faults?
I don't have specific insight into that. I know we do have a lot of debug features. In particular, the ECC error detection. Any cache error that's detected gets logged, and software can keep a tally of those and report if we're detecting errors.
Does that appear as a PID in OBD2?
That's several layers down the
Yes.
supply chain beyond what I have familiarity with.
It'd be interesting to know.
Yeah,
because,
yeah,
I mean,
I agree.
it's gonna really have a profound effect upon what kind of penetration these products are gonna have, because if they're not really serviceable,
Mhm.
it becomes almost a non-starter. It's really tough.
That's a good point.
Yeah.
Okay, so to make the I6500-F, we've extended parity protection through more buses throughout the system, and the cluster level status and control registers now all have parity protection. All of the externally facing buses now have parity protection. We've added a bus timeout mechanism if a bus request doesn't get a response in time. We've added support for runtime built-in self-test, and I'll talk about that in more detail in the next slide. And the last one is also pretty important. There's a dedicated fault reporting bus. So the issue here is, if we just relied on the conventional mechanisms, if the processor detects a fault and tries to communicate that by writing to a memory mapped I/O location somewhere or something like that, there's a risk that that fault could actually obstruct that path that we're trying to use to flag up a warning that we're having a problem here. So we've added a dedicated fault bus that's used only for reporting faults to minimize the risk that a fault would be detected, but that warning would be blocked.
So there's a separate controller or micro CPU that pays attention to that fault bus?
Right. Now that's another part that's the customer's responsibility to design. On their SoC, they would have some fault controller that is very high reliability circuit that is monitoring these signals and taking the appropriate action. And it could do things like it could reboot the system, or take it offline and fall back to a spare system, or signal that the car should pull over and stop, or there's a lot of options depending on what the customer wants to do in that case. Yes.
So functional safety is a close cousin to secure computing.
Yeah.
So like credit card computing.
Mm-hmm.
And so having done some of that work before, I've always wanted something that verifies execution is done correctly. So here you're checking data transmission errors or data corruption. but not really program flow corruption,
Mhm.
where there might be a fraudulent instruction inserted or a omission, like a program counter
Yeah.
error.
Okay. This talk is probably too long as it is, so I didn't actually go into that. But MIPS does have another processor, another product where we have a smaller processor that it goes with a secure boot system. So the hardwired boot code checks the cryptographic signature on the boot ROM before booting up, and has secure control and root of trust. Maybe you've heard of root of trust or secure execution environment. We have those things. The i6500 series also has support for hardware virtualization, where you can run software or even an entire operating system in a contained sandbox. And so you can have multiple programs running on the processor that are isolated from each other in hardware. That is one use for that is security, where you have some code running that you may not necessarily trust. You want to be sure that it doesn't wander off and mess with other things in the system. You can use virtualization for that.
So I guess the one thing I don't see on the list that I've seen used a lot for space missions is redundancy. Do you have any capabilities for doing redundancy maybe with like 2 CPUs?
Currently not with the i6500 series. So yeah, that is the next logical step. We'll talk about that a little bit more, just a little bit further on. But yeah, and that is one thing that is commonly used is the running dual cores in lockstep to detect if something is.
But also that redundancy could be done by the customers at the CPU level. Like two of those, they can do that.
Right.
Or three.
And going back to the earlier picture, with the computing flow where there's that upfront perception block that's processing the sensor data, that also has some redundancy. If you have camera system feeding in plus a radar or a LiDAR, you have some built-in redundancy there as well with diversity, not just a replicated copy. So depending on the application, if the demand is that high that you need full lockstep dual.
So from in some sense, it seems to me that this stuff is almost bound to be more reliable at the hardware level than the things people build on top of it. Isn't that really true?
You mean like in terms of like?
Well, I would be more inclined to expect catastrophic errors from the software that runs on this than from the hardware.
Yeah, possibly. So some of the features like the watchdog timeout and things like that can also deal with software issues. If the software gets into a deadlock or something, that will get flagged up. So there are ways to deal with that at a little bit higher system level.
You can help that too.
But that is definitely an important concern that plays a part here.
Phil, so how do they, one thing I keep thinking back to is, if all else fails, just pull the car over to the curb.
Mhm.
But you need some intelligence left to pull the car over to the curb.
Right.
If you get into a main process deadlock or something, how are you going to do that? So that would seem to be screaming for redundancy or something.
Right. So that goes back to this diagram. The things to the right in the orange boxes are more safety critical and need a higher standard of reliability, and the things to the left are a little bit less critical. But yeah, you're right. Things like triggering an airbag, you can't take that back. So the controller for that has to be very reliable.
But once you say trigger the airbag, it happens quickly.
Right.
If you trigger the activity to pull the car over the curb, there's still another billion instructions that have to be executed in order for that to happen, right?
Right.
It's 10 seconds worth of high power computing that still needs to happen.
Yeah. So yeah, if that's your recovery mechanism, you need to have capacity and reliable backup capacity to be able to do that. But if you have, say, 2 redundant vision processing systems and one of them goes bad, you can then say, okay, well, I don't trust driving another 100 miles with just one vision processor, but I can drive for another 10 seconds or 30 seconds to safely pull off the road.
a follow-on to that, just curious, what is in a car today? There's several cars out there, you use Tesla, but Subaru's got a number of systems.
Yeah, Nissan.
Are the cars today redundant, or do they just build a highly reliable CPU?
Well, so the ones that are on the road today are really not rated as fully self-driving. You know, the driver is supposed to be still paying attention and, you know, watching out. So if something goes wrong, the driver is supposed to be able to.
So today the redundancy is the person sitting in the driver's seat.
Well, it's not quite as bad as that. There is also a lot of redundancy.
Well, it's okay. I mean,
But you're right. It's not the cars that are on the road right now. A lot of these things are not redundant to the level that you would need if there was no steering wheel. So.
Well, I guess it's even asking, is there redundancy just in the ADAS features they have today, with the adaptive cruise control with the automatic braking, that doesn't have redundant process in there?
Yeah, no, you know, this is getting a bit further down the supply chain and I don't know the intimate details, but you know, sure, the part that's making the decision to say, okay, slam the brakes on now has to be more redundant.
I mean, surely it's not just redundancy, you also
Yeah.
need isolation.
Right.
I mean, you need to be sure that whatever's controlling your brakes is gonna work even if the vision doesn't work. And that you get by isolation.
It's gotta be almost like a panic module, you know?
Yeah.
It's time for you, panic module.
You mean the thing that Boeing doesn't have in the 727?
I'm wondering if somebody can bring that up, but yeah, so the airplane is going up and, you know, the pilot's trying to pull up, the airplane's trying to pull down.
Yeah.
And obviously they haven't thought through the, the whole system of redundancy.
Right, yeah. Yeah, of course, all of these factors need to be taken into consideration and the microprocessor is just one piece in the big system.
Does your company focus at all on the way you introduced this as a system problem, and you've kind of focused on a piece of the technology?
Mm-hmm.
I'm curious, is your company involved with more of the system level aspects, or how involved would they be?
Not greatly involved. Like our marquee example is Mobileye, which is now part of Intel.
Okay.
You know, and they put a lot of effort into figuring out not just how can we build a chip, but what does it really take to reliably drive a car. And you know, we have interactions with them to be sure that we understand what do they need from a microprocessor. But yeah, we don't really try to get our heads around the whole problem of driving a car to the level that we can be making those technical decisions.
So by the end, they decide how many processors to put in their system to
Right,
make
absolutely.
safety and redundant, right?
Yeah. So one of the more interesting features that we've added for safety in the i6500-F system is runtime built-in self-test, logic BIST or LBIST for the CPUs. To give a little bit of background, this reuses some of the design for test logic that is typically used in manufacturing tests to screen out faulty parts before they go to the customer. And I'll just give a quick background of how that works. So in a digital logic design, when it's in test mode, the registers or flip-flops in the design are connected together in a what's called a scan chain, which is basically just a big shift register. And the test system is a big piece of hardware you stick the chip in, and it scans test patterns through the chip, and then those test patterns propagate through the functional logic of the chip, and then you scan the result back out and compare it to the expected data. And so these test patterns are pre-computed and stored on the tester, and nowadays they're pretty large to take a lot of storage. So built-in self-test replaces these targeted pre-computed test patterns with a pseudo-random test pattern. So you have on-chip a LFSR, or pseudo-random pattern generator, that scans data through this scan chain. And then you have a signature recognizing logic that keeps a cumulative signature, so effectively like a checksum of the results as you sequentially run many of these random test patterns. And since the pseudo-random test pattern is actually deterministic, you can pre-calculate what the final signature should be, and then compare and see if it passes or not. And so this is widely used, and in chips today, and it's typically targeted for like a power-on self-test before the chip starts functioning. During reset, it will run these tests. And there is CAD software that will automatically insert these scan chains and the test logic into the design during the logic synthesis flow. So to be able to do runtime LBIS testing on the CPUs, there's a couple of things we need. First of all, we need sufficient performance headroom that we can afford to take one CPU offline and run tests on it while the overall system is up and running. So we have the ability to do that and to go through and test individual CPUs in a round-robin sequence while the system is up and running. The other capability, and so one, as the diagram at the bottom illustrates, the important thing here is that there's this fault-tolerant time interval that I mentioned earlier. You have some interval of time from when a fault first happens before you can expect that it would actually cause a dangerous safety condition. So you need to detect the fault and take corrective action before in less time than that interval. So you need to run the self-checks periodically, and then there's a certain amount of reaction time once you find a failure to do something about it. So the sum of the test interval and the reaction time has to be less than the fault-tolerant time interval. So since this is periodic testing, it also naturally has the weakness that it doesn't detect transient faults, and in this particular application that was deemed as an acceptable risk. It leverages the ability that I mentioned earlier. The cluster power controller has the ability to take an individual CPU offline and power it down when the system is running. And it's important to logically isolate it from the cluster so these random test patterns that are going through the chip that's being tested don't propagate out into the rest of the system and corrupt things. So we made use of that capability to enable runtime testing. So the process is software first has to initiate a cache flush and write out any modified data from the processor's cache out to memory, and then take the processor offline, and then trigger the BIST logic to run the test. And then once the test completes, hopefully it passes, then the processor basically reboots and then rejoins the system.
So this interacts with the coherent system as well?
Yes, to the extent that if there's data in the processor cache that's modified that hasn't been written out to main memory, even whether we're just doing a power down or whether we're doing BIST testing, we need to, make that data visible in
So
external
the
memory.
graphics processors will go and refetch it?
Yeah. Or if some other CPU in the cluster needs to use that data or whatever, you need to have it written out to the L2 cache or to main memory before you can take that processor and its L1 cache offline.
So can the built-in self-test also test like the neural networks as well, or just the CPUs?
So in this kind of system I've been talking about, the neural network is running in an external hardware accelerator, whether it's a GPU or a DSP or some other accelerator. So that's that's a block from a different supplier. So that's out of our purview how they test those. They could use a similar scheme or. So once we've designed a system with safety features, how do you get it certified that it's safe, and why does that matter? Like many standards, it adds overhead to the engineering task that people don't always like. This is kind of the family-friendly description of that. But the ISO 26262 standard for functional safety for automotive electronics is an international standard that for automobiles. And it's based on a systematic analysis of risks and coming up with mitigations for those risks throughout the product life cycle. The goal is to reduce the risk to an acceptable level and then follow it through the process to be sure that the end product actually has the targeted risk level, that your safety features you put in are effective and operational and make it into the end product. It's not a legal requirement, but in Europe in particular, it reduces product liability, showing that you use components and follow a design process that's certified, can show that you're using the state-of-the-art best practices and to design your car, and so that reduces the product liability. And it's getting pushed increasingly further down the supply chain. And the electronics in cars are becoming more and more complicated, that the car manufacturers and now even the semiconductor companies, chip manufacturers, don't know the intimate details of the design well enough to be able to do the exhaustive analysis of the designs. So they're pushing this analysis further down the supply chain to where now it's also affecting the IP suppliers as well. And the most recent edition of the spec adds the safety standard adds a new chapter specifically dealing with how to apply this to semiconductors. And you can get your design certified by third-party assessors, such as this company called Resultech that we've used to certify the I6500.
Our last meeting was a tour of Woodward, and they're talking about their software, and they're doing it in flight control, engine controls, and stuff. And they talked about some process where every single line of code has to be justified, and you have to trace every branch. And so I guess you can do the same thing
It's
at the hardware
a
level.
little bit less intensive than that, but the same basic idea. I'll talk about that in the next slide.
Is this kind of similar to where, like software, where the design process is as important as actually the output?
Yeah,
Testing?
yeah, exactly. Yeah, we'll be getting to that in the next slide. We're almost to the end, so I don't see too many people falling asleep, and we're getting good questions, so hopefully I'm not boring you too much. But the end is
It's the beer, not your talk, that makes us sleepy.
So the ISO 26262 safety standard addresses two types of faults. There's random faults, which is a case where the design is not functioning the way it was designed. Either it wears out and deteriorates and starts to fail, or some random event like a cosmic ray or signal noise or power supply variation or something introduces an error that affects the operation. And that's dealt with by analysis and by safety mechanisms to detect or avoid or recover from such faults. And then the other type of fault is systematic faults, where effectively there's a bug in the design. It doesn't work the way it was intended to, or doesn't meet the requirements. And that's addressed by the development process and traceability that you guys have been just asking about.
So what do you do about a random fault in your pseudo-random number generator that's testing everything?
Well,
I mean, that's a serious question.
sure. So, any logic in the chip could have a fault,
Right.
Including your safety measures and recovery measures. And so that's part of the process, is assessing, what is the probability that there's a fault in your baseline logic? What is the probability that it would be detected by the safety mechanism and dealt with? What is the probability that the fault would be in the safety mechanism itself? And all of that feeds into the overall safety level.
Roger, you're kind of protected by, there's huge redundancy of faults usually in patterns that find faults.
Yeah, right, true.
Many other patterns will find the same fault.
So one key component of the safety standard is what's called the Automotive Safety Integrity Level, or ASIL, which is an abstract categorization of the inherent safety risk. And it's composed of three elements. There's the severity, which is basically the extent of the injury that would be expected if an accident happens. The exposure, which means the probability that that fault could actually happen in practice. And controllability, which means the chances that the driver could take some sort of corrective action and recover and avoid an accident if the fault occurred. And so using these three factors, you come up with a composite ranking of the risk. And they're categorized in three levels from A through D, for lowest risk to highest risk. So the level D, ASIL D, typically are systems that require full redundancy to be able to continue operating in the presence of any fault. HLD is another widely used one that is more at the level where you need periodic self-checks and you need to transition to a safe state if a fault occurs. That's usually sufficient to deal with an ASIL B level of risk. And there's also, reliability theory. If you have a system that is highly reliable, it can be composed of components that are at a lower reliability level if you have sufficient redundancy or error detection or dealing with it in an appropriate way. And so a component that individually is rated at an ASIL B level can be used as part of a larger system that's rated at an ASIL D level. And that's denoted as ASIL BD, as shown here, or ASIL B decomposed from D is how it's sometimes described. One other concept that's important here is the safety element out of context, which is very applicable for reusable IPs like a microprocessor. And this is where a component is designed for general use and not for one specific targeted application. So in that case, the designer can't specifically target the particular safety requirements of every use, and so it's classified as a safety element out of context. And so the MIPS I6500-F processor is classified as a safety element out of context and certified as the ASIL BD level. I forgot to mention, proven in use. Other nice thing happens if you're designing a general purpose component. If it's been used successfully in other applications, then that increases your confidence that the probability of a systematic error is less. So that also affects your safety. So putting all of this together, how do you get the design certified? First of all, there's a lot of training involved, and in particular, you have to have a designated functional safety manager on the project who's been through the appropriate training. Early on in the project, you do the hazard analysis and risk assessment where you assign the ASIL level for your function. And then using that, you determine the safety requirements based on the safety goals. And then from there comes in the traceability, like you were talking about. Now this isn't traceability from every single line of code. This is traceability at the feature level. So every feature will have to be, that's safety relevant, will be called out from the spec and has to be followed through the design implementation, the verification plan, verification results. It could be functional coverage metrics to show that your test actually exercised the function that you're trying to test, and then through to the product documentation. And that's traceability both ways, from the spec through to the result, and also from all the tests backward to exactly what point in the functional spec they're supposed to cover. Once you have the design in place, you do the failure mode effects diagnostic analysis, or FMEDA, which is a quantitative analysis of the risk of the and failure modes and safety mechanisms. So one component that's widely used is fault simulation. Once you have the design and you've done simulations to verify that it works correctly under normal conditions, you can rerun the tests while randomly injecting faults into the design. And there are specialized EDA tools that do this. And you can get an estimate of the probability that, or the percentage of the faults that are handled appropriately by the safety mechanism, or that are invisible and don't show up at all, or what percentage of them actually manifest as a failure that would be visible at the outputs. So that's very quantitative, but it can also be misleading. There's always chances that you're not actually running the stimulus that you think you are and not exercising things that you think you are. So it needs to be backed up by some other more manual types of analysis. Like diagnostic coverage estimation is where you have a safety feature like ECC on your RAMs or something like that, and you can estimate from the design itself what fraction of the design logic is covered by that safety feature. You can do things like fault tree analysis, where you start at an output and work your way back and analyze what conditions could contribute to that output taking on an incorrect value. And dependent failure analysis, where one element can fail and it may not immediately cause a safety problem, but it can provide incorrect inputs to another element that could then, as a cascading effect, produce the incorrect output that could be a safety problem. So all of these kinds of analysis go together and are summarized in the FMEDA report, which is included in the safety documentation package with the product. And that concludes my talk. I'll get into any questions now. Thank you, everybody, for being an attentive audience.
Yeah, so I work in the semiconductor industry, and wave computing is kind of new to me. Could you tell us a little bit more about wave computing, like
Sure,
how long
yeah.
they've been around, and what else they do other than MIPS?
Okay, so they're a startup company. I think they were started, I forget, somewhere around like 2010, 2012, somewhere in that range. Focusing on this coarse-grained reconfigurable array style of computing that I mentioned earlier. And they've are targeting that for artificial intelligence and mostly neural network processing. And they design both the RTL design, and then they design make chips and systems. So they have neural network and artificial intelligence compute accelerator systems that are in customer testing right now, that you could get a either rack-mounted system or a desk-side big compute appliance that your data scientists can use to run their neural networks on. There are a number of startups in that area, and they're seen as one of the ones that are closest to being real products and not just vaporware. So they've got pretty good venture capital funding, and last year they acquired MIPS for the MIPS processors complement the neural network accelerators like I described in the presentation, and they were actually a customer for a little while first before they acquired us. So yeah, that's what Wave is about.
Where are they located?
They're in Campbell, California, which is in Silicon Valley.
Okay. But you work out of...
I work out of Fort Collins. Yeah, I worked in MIPS in California for about 6 years, and then got a chance to move back to Colorado. So I've been telecommuting since about 2012, as MIPS has gone through a couple of corporate transitions now. So yeah, so now I'm working remotely for Wave.
So I've seen the diagnostics used as a mitigation strategy in FMEAs before, but I've never actually seen that combined the acronym, the FMEA, EDA, whatever. Is that something that's part of the ISO 26266 standard, or is that something that came from something else?
I think it's part of the standard. It's definitely, we used the Resoltech certification company to certify it, and that's one of the things that they had us go through. Yeah. I believe it's from the standard, but I didn't want to promise that.
I just haven't heard of like the diagnostic coverage used as part of an FMEA analysis. So it's interesting.
I believe so. The FMEDA is like a step after the FMEA. Any other questions?
This is way at the other end of
Okay.
the world in terms of the end product. I'm just curious when somebody implements your stuff in silicon, what is the operating range, temperature-wise, that those chips are spec? I mean, I know what the mill spec is, this and that and whatever, but some people drive their cars at 40 degrees just like trying to start a tank, in the military. So, is it pretty much a mill spec kind of a part?
That's really up to the customer.
Well, I know that.
I mean,
I'm just calling upon you with your knowledge of the business to speculate what.
Yeah, I mean, our processors are used in a wide range of applications. We did have one processor that was used in a satellite by a Japanese space agency, I believe. So it would have to be, outer space radiation hard. Like I mentioned earlier, Microchip makes microcontrollers that use not the I6500, but other MIPS processors that, they have wide range of, ones for different operating.
I worked as a reliability engineer for a long time and dealt with some automotive customers, or we dealt with some suppliers to automotive customers, and they said that automotive is tougher than military. That was the opinion.
And it doesn't affect just this kind of stuff. If you drive a heavy SUV on a road in the middle of Saudi Arabia and you have conventional U.S. tires, they will usually or frequently blow out from the heat. I mean, literally, they'll explode. They'll come apart. So the whole car has these kinds of problems.
but actually in the automotive there are two main categories. One is the so-called cockpit, and then the ambient is 50 and 85. And so you calculate what is the junction and everything.
Yeah.
And then the other one is 125, which is kind of under the hood.
Under the
So-
hood, right?
Yes,
Yeah.
yeah. So probably your customers decide where
Sure, where they're gonna
to go.
Okay.
Okay.
Hey, thanks very much.
Thank you, everybody.
Yeah,
Appreciate
very
it.
well done.